Hello, I'm Barry Sullivan, Director of Program Development for the Electrical and Computer Engineering Department Heads Association. It's my pleasure to introduce this spotlight session from Analog Devices, which will be presented by Sam Fuller, Vice President, Research and Development and Chief Technology Officer of Analog Devices, and Kathleen Meehan, Associate Professor, Bradley Department of Electrical and Computer Engineering at Virginia Tech. And they will be speaking on Tinkering 101, inspiring students with hands-on learning tools and techniques.
Barry, thank you very much, and it's delighted to be here this morning. Thank you all for coming. And you've had a bit of an introduction to what we're going to talk about. Cole, I think, gave a good description of it, but we're going to go into a little bit more detail and describe what the Analog Discovery Kit is. And I thought, for getting started, I would just give you a sentence on who Analog Devices is and why we might be interested and involved in this. And Analog Devices is a company which is focused on high performance and high precision signal processing. And to do that, we've got a whole set of integrated circuits that run from converters to RF, digital signal processing chips, MEMS, sensors, and other linear ICs. And that rounded out turns out to be a business for us at about $2.7 billion per year, with about 3,200 engineers that provide the work and the intellectual input to be able to produce those numbers of chips. And one way I describe ADI is you'd be hard-pressed to find any wireless base station in the world that doesn't have ADI converters and various other RF and other chips inside them. So that's who we are, and that's what we do. But what I want to talk about today, along with Kathleen Meehan, is the Analog Devices University program. And as was described earlier today, it's meant to be an active, hands-on, anytime, anywhere lab kit to let undergraduates get an exciting introduction to electronic design. And that's really why we've done it. I mentioned in the industry panel yesterday that over the past decade we've seen a bit of a trail-off in students coming out with understanding the fundamentals and the practicality of doing analog or electronic design. And we wanted to do our part to try and reverse that trend. And exciting the students is certainly one of them. And the ultimate goal here is to have these students better prepared, potentially to work for us, but I think more importantly, as most of these students don't work for us but go out and work for our customers, to have them at those customer sites able to do credible and competent analog mixed signal design. And also from our point of view, it's a way to introduce students to ADIs, high performance and high precision integrated circuits, so that they can see the range of sort of sub-assemblies or modules that are already available to them in doing their design. So that was our motivations. And so I've got just a couple of photos here to try and describe the reality of this. This is the Analog Devices module, which is comes in this kit, and it was described as available to students for $99. And in it are the electronics that allows it to have several trace scope, a couple of signal generators, a logic analyzer, waveform analyzer, spectrum analysis as well. So it's a fairly small plastic package with some very high performance integrated circuits inside of it, with a whole set of probes to power, drive, and then measure the breadboard part that the student has got. And then the other critical part of this is that that instrument is is connected by a USB cable back to the student's PC, and that USB cable provides all the necessary power for driving the device, and then provides the software interface. So on the Windows PC, you can see that they've got both the soft oscilloscope as well as the images of the waveform generators, spectrum analysis, and so forth. And this is this particular slide uses the software that one of our partner Digilent has provided, so that in this single, under $100 kit, they get both the software that they need as well as this, the hardware to be able to drive that. And over the past week, we've announced another partnership with MathWorks, and it was described just in the last Spotlight session. Many of you, as you've used MATLAB and Simulink for some of your courses, they've now extended MATLAB so that it can drive this analog discovery kit as well. You know, I would say sort of a fundamental idea we had going forward was we wanted to maximize the utility and the ability to scale this across all of your universities, and so it's an open software interface. So it actually began at RPI, and there's software that RPI has developed to drive this. We then have worked with Digilent to get a broader set of software to support it, and now you know, MathWorks has come with MATLAB to support it. So the hope is that it's with an open interface, you give a variety of software available to drive this, and at your own school, as you have ideas, you can extend that yourself. Now, in order for the student to be able to run the labs and do the experiments, in addition to the instrument itself, the software to support it, there's a analog discovery kit that provides the various you know, passive components, RLs and Cs, as well as diodes, potentiometers, transistors. More than 20 integrated circuits, from op-amps through converters to some power management parts from ADI. And it's designed to have all the components you need for all the labs and experiments that I'll describe in a moment that are available in Circuits 1 and Circuits 2 classes. I'm told that we have enough of these at the expo next day, so that if you are interested in this and you go to the Digilent corner, they give you one of the basic kits here. We'll back it up with some components, and all the software is downloadable off the web. And you know, while I think it's exciting to talk about the capabilities of the hardware instrument and the software behind it, there really is a set of other essential collateral that in order to make this useful. So I won't work through the topic on all of these on the list here, but you know, one of the great things about this is this had its genesis with one of our senior designers, Doug Mercer, who's here, and you can drop by our booth and talk to Doug. But he started by trying to improve you know, electrical engineering education at RPI. And in doing that and developing sort of an early prototype of this, he developed a lot of lab exercises. And then other people have come in and developed additional lab exercises. So there's a lot of collateral material that you can pick from in order to make your actual hands-on tinkering experiment with your students really an interesting experience. And so after those visuals, again, just coming back to the summary on this, the intent here is to have hands-on independent learning. You know, you're less dependent, the student is less dependent on the fixed hours of the lab when it's open, whatever instruments might need to get shared in the course of that lab. But being able to do it on their own time, anywhere, I think it provides a level of being able to explore, as we say in the title, do some tinkering, but get a better intuition of what goes on. And I mean, our hope is that it provides a really good complement to the analytic skills that get taught in the classroom and in the lectures by having students work with this. And again, our intent was to get this at a low enough price that it was really accessible by any student going through an engineering curriculum. It's under $100 for the instrument. I think it's another $40, $45, $50 for the various parts kits, depending on which part kits you get. But that's meant to be enough to be able to go all the way through electronics 1 and 2, and actually potentially use that later on in the higher level courses. I would say, as we've introduced this at ADI, I've got several engineers that are, you know, have 10, 12 years of experience, and they said, gee, you know, rather than have to share this oscilloscope with the guys in the lab, I'll just get one of these and do some quick checking with this, and then when I do my final design, I'll go on to the more expensive instruments. It's been eye-opening how broadly this has been accepted. And then I'd like to make one more point before I turn this over to Kathleen, which is we think the really power of this is once you provide the basic instruments of a scope and a signal generator, logic analyzer, and so forth, that then providing by a set of open interfaces, you really maximize the ability for us to be able to begin working with a growing number of partners to make this applicable in a number of different applications. And I would really say out to your departments, it's a chance for you, some of your TAs, potentially some of your undergraduates as well, to come up with great innovations, do some extensions on their own, and you can make the software and the experience of this specialized to your particular department and the particular expertise or specialization that you've got at your university. And I think with most programmable software systems, and this is extended through the hardware design as well, having an open interface where you begin to build a ecosystem, and it's impossible to tell where that will go in the future. But the hope is that this really grows into something that is useful to all of your ECE departments. So we've had this. This is announced about a year ago. We've been quite pleased with the interest at universities. We've got this has gone out now and it's being used in labs or it's through some student tinkering at 50 universities within the first year, and we would expect that we'll continue to scale this. We have a focus really in U.S. and North America, but we will scale this, I think, globally over time. And what I would like to do to try and reinforce the hands-on tinkering value of this is turn this over now to Kathleen Meehan at Virginia Tech, who has been one of the schools that has been one of our best partners in trying to use this equipment and figuring out how to make it, how to use this to excite the students and help the students in their learning. So Kathleen, I really appreciate you being here, and let me turn it over to you.
Thank you, Sam. Sorry, I've got still laryngitis. What I'd like to do is first go through quickly why we're interested in this from a teaching perspective. If you look at how students learn, there's a number of different theories, but one that says that they learn by hearing, seeing, and also by actually doing or being involved and putting hands on in the learning activity. And unfortunately, the only activity that we have in our electrical and computer engineering curriculum that's really hands-on is our experiments. And so what we're trying to do at Virginia Tech is expand the number of hands-on activities that we have in the curriculum. Oops, excuse me. Okay. The other reason that we need to do it is based upon a study that was done in 1987. Students don't remember what we talk about up in lectures, and they at least learn a little bit more when they read or they do the problems, but the best way to have a student learn is to have them actively engaged in the learning by having them explain what they've been doing and particularly explain what they're doing as they do it. And this is what we do in our experimental laboratories. So what I want to do is give a quick example of one very simple experiment that we do in our first circuits lab. It's a square wave generator, so we can cover a set of topics. Not all of these are in each experiment that we use. We make modifications every semester of how we use this square wave generator. We'll talk in PSpice about when does the oscillation start because it's a non-ideal op-amp, or we'll talk about applying an initial condition to the capacitor and show that it starts oscillating immediately. Okay. I also have just a quick movie, but I'm not going to play very much of it, that shows that we put visual cues into the students' experiments to show how things work. Whoops. And I'll go through There's where they actually make the measurement from the oscilloscope to show how, again, where the square wave gets initiated and how the charging on the capacitor or the voltage on the capacitor charges and discharges. We ask that the students develop MATLAB code to explain what in their analytical framework, how the voltage across a capacitor changes, as well as the voltage on the output of the op-amp. Oops. Oh, that worked well. All right. So we also have, and I don't know why these images didn't show up, but we also have now, because of the app that's with the MATLAB, the ability to import data directly from the oscilloscope and overlay it on the MATLAB code that they have generated. And in a later experiment, we also have them write a function out to the arbitrary function generator that's a sum of the Fourier components so that they can physically see what the square wave looks like, compare it to an ideal square wave, and also look at the spectrum components in that to show that the sine waves still are there when they see a square wave coming out of the oscilloscope, or the function generator. We're also using this to wrap up, to stimulate designs, and we run a competition every year to try to generate internally a lot of teamwork and independent projects by the students. Thank you very much.